Good morning, I am Mr. Ish. A very important concept and video here because understanding this can save you a lot of time with some differential equations. The limiting factor for Bernoulli's equation, or better yet, what is that factor if it were absent from a differential equation, a first order differential equation, that you would not have a Bernoulli's equation? Let's examine that. When you're looking at something of this form, dy or dx plus py equals q, you know you have the linear style of differential equation. It's first order because of the representation here being y prime. When you make a slight modification to this, dy over dx plus py is equal to qy to the power of n, now you have a Bernoulli style equation. But what is it, that factor which comes around over here that makes you examine something with regards to this specific style of differential equation, a Bernoulli's form? Or what would it be in terms of a factor that if you didn't have it, then you could not use the Bernoulli style of differential equation solving procedure? And I'm going to tell you that. Consider perhaps the most basic style of what we would think to be a Bernoulli's equation. We would have dy or dx plus y is equal to, let's just bring in an x which would represent your q, and let's bring in a y. Because it kind of looks like y to the power of n, except here you have y to the power of 1, which you don't even need to notate. At first glance, a student may perceive this to be a Bernoulli's equation because it looks slightly similar to that, or it looks similar to that. Then you go around and you start doing your procedure. You know, with the Bernoulli style equation, you're looking at a z substitution which is always equal to y to the power of 1 minus n. The n over here being 1, as you see there's a 1. You see that z is equal to y to the power of 1 minus 1, which is y to the power of 0, which is 1. So you say z is equal to 1, then you do a derivative of z, and then you say derivative of that is a 0, dy over dx. Then what you would do is divide everything here by y, because that would be the procedure you would utilize for this style of equation when you're solving it. You'd end up arriving at this y to the power of minus 1 dy over dx plus 1 is equal to x. The problem is when you look at this and you start comparing it to this, and you know you would technically multiply everything here with the coefficient right here. There's a specific coefficient, you'd multiply it with that coefficient. That coefficient here is really a 0. You could zero everything out. And then you start looking for some of these commonalities. You see z is equal to 1. We can bring in a z over here if you want it, a z. But then we look at dz or dx is equal to 0, dy or dx. It's not fitting over here. You cannot bring in a dz or dx, and the whole procedure fails. The procedure fails because this in reality was not a Bernoulli style equation, because there's an absence of a factor. The presence of that factor would have made it a Bernoulli's equation, but the absence of that factor makes it nothing more than just a regular question which is not of a Bernoulli style of differential equation. And what is that factor? That factor is not the presence of y to the power of n, but is very specifically the presence of n. To have a good Bernoulli style of equation so that you can solve it in the related procedure as you would want to, that n must be greater than or equal to 2. A factor which is, or let's say a concept which is not routinely stressed or emphasized for the student, so sometimes they can take a wrong route. What in reality you would do over here would not be a Bernoulli style of solving procedure. You would just do a basic separation of variables, and you can clearly see that to be the case, because it's very easy when you're looking at everything in that regard. You're looking here at dy over dx plus y is equal to xy. You take the y on the other side. Dy over dx is equal to xy minus y. Dy over dx is equal to y. You isolate x minus 1. When you isolate x minus 1, you can take the y on the other side. You have 1 over y. Dy over dx is equal to x minus 1. You can integrate this now. When you integrate it, you have natural log y come over here, and here you'll have an x squared over 2 minus x plus c. Therefore y is equal to, in terms of a function which represents this differential equation right over here, this would be e to the power of x squared over 2 minus x plus c. This right here would be your answer, but you didn't solve it by utilization of the Bernoulli style of procedure. You solved it by separation of variables, because this question was not a true Bernoulli's equation, because here this exponent n was not greater than or equal to 2, which is the most important part. Remember, if that exponent y over here was 2, then you would do z is equal to y to the 1 minus n, which would be y to the 1 minus 2, which would be y to the power minus 1, which is good. Now you can do a derivative. dz over dx of this is equal to derivative of that, which would be minus y to the minus 2 dy over dx. This little coefficient here is what you could then multiply across and then bring in these substitutions. Your substitution would very well fit in. You'd have this substituted by this, you'd have this factor right here substituted by z, and then you would have converted a true Bernoulli equation into a linear style of differential equation. But remember, the factor or the limiting factor you're looking for is this: n must be greater than or equal to 2 for the term y to the power of n. That n is most important over here, so keep that in mind. And thank you for watching this video.